If you've ever asked, is this trend real or just noise? You're already thinking like a statistician, because statistics is the difference between a guess and a grounded conclusion, a viral claim and verified evidence, a random outcome, and a measurable pattern. In a world flooded with numbers, statistics is how we turn data into decisions. What is statistics? Have you ever wondered how your favorite streaming service knows exactly what movie to recommend next, or how public health officials can predict the spread of a disease? Maybe you've seen a news report about a political poll and question how they can know what a whole country thinks by only asking a few thousand people. The answer to all of these questions and so many more lies in the powerful field of statistics. It's a discipline that touches almost every aspect of our modern lives, often in ways we don't even notice. So what is it formally? Statistics is the science of collecting, organizing, analyzing, interpreting, and presenting data to support decision making under uncertainty. Let's quickly break that down. Collecting is about designing studies and gathering information. Organizing involves cleaning and structuring that raw data. Analyzing is where we apply mathematical tools to find patterns. Interpreting means figuring out what those patterns actually mean in a real-world context. And presenting is all about communicating those findings clearly to others. In plain language, statistics helps us learn from data, even when the information is incomplete, messy, or noisy. Think of it as a toolkit for navigating the fog of uncertainty. Data in the real world is rarely perfect. It's often chaotic and filled with gaps. Statistics gives us the methods to cut through that noise, to find the signal hidden within, and to make sense of a complex world. This is why a statistician doesn't just do math. A statistician is more like a detective using data as their clues. They start by asking a series of critical questions. First, what question are we truly trying to answer? This is the main portionist. A precise question leads to a precise answer. Are we trying to increase sales or improve customer satisfaction? They sound similar, but they require very different approaches. Second, what data do we need and what's missing? Once the question is clear, we can identify the necessary information. Do we have it? Is it accurate? Are there biases in how it was collected?
Recognizing what's missing is just as important as using what's there.
Third, what method is appropriate and what assumptions are we making? There isn't a one-size-fits-all formula. Choosing the right statistical test is key.
And every method comes with assumptions, conditions that must be met for the results to be valid. A good statistician is transparent about these. And finally, fourth, how confident are we in the conclusion? Statistics rarely gives a simple yes or no. Instead, it provides a level of confidence. It helps us quantify our uncertainty, saying something like, we are 95% confident that our result is not just due to random chance.
Because the goal isn't just an answer. The goal is a reliable answer. It's an answer backed by evidence with a clear understanding of its strengths and limitations. That's the true power of statistics. Why statistics matters? Here's the hook. Most real-life decisions happen without perfect information. Statistics is the tool that helps you make the best decision anyway. Whether you're running a school, a business, a clinic, or a content channel, statistics helps you submit patterns, test claims, predict outcomes, reduce risk, measure impact. The two main branches of statistics. One, descriptive statistics, what the data says. Descriptive statistics summarizes and describes what is already in your data set. Think what happened. It includes measures of center, mean, median, mode, measures of spread, range, variance, standard deviation, data displays, tables, bar charts, histograms, box plots, distribution shape, That's skewness. Outliers example. A school summarizes exam performance, average score, highest score, score distribution, and how many students passed. Descriptive statistics doesn't explain why things happened. It tells you what happened, clearly and accurately. Now, let's explore the second major branch of statistics, inferential statistics. This is where we move beyond simply describing our data and start asking, what can we conclude beyond the data we have? At its core, inferential statistics uses a small, manageable sample to make informed conclusions or inferences about a much larger population. Think of it like a chef tasting a spoonful of soup to judge the entire pot. It's impractical to drink the whole pot to see if it's seasoned correctly, right? The spoonful gives the chef enough information to make a confident judgment about the whole dish. In statistics, we do the same thing, but with data. While descriptive statistics tells us what in our data set, inferential statistics helps us predict what's true for a group we haven't fully measured. It's the bridge from the known to the unknown. Always asking the question, what does this data suggest about the bigger picture? This branch is home to a powerful toolkit of methods. It includes, first, sampling and estimation. This is the foundation. It involves selecting a representative sample and using its statistics, like the average, to estimate the population's true value. Next, confidence intervals. Since our estimate is based on a sample, it won't be perfect. A confidence interval gives us a range of values where we believe the true population parameter lies, along with a level of confidence like 95%. Then there's hypothesis testing. This is a formal process for using sample data to evaluate a claim about a population. For example, does a new teaching method truly improve test scores, or was the observed difference just due to chance? We also have correlation and regression. These methods help us understand the relationship between two or more variables. Correlation tells us if they move together, while regression allows us to model that relationship and make predictions. ANOVA, or analysis of variance, is used to compare the means of three or more groups to see if at least one group is statistically different from the others. And finally, prediction models, which use historical data and regression techniques to forecast future outcomes, like predicting student enrollment for the next 5 years. Here's a practical example. Imagine your school district is considering a new learning management system. It's impossible to survey all 10,000 parents. So, you survey a random sample of 200 parents. You find that 70% of your sample supports the change. Using inferential statistics, you can then estimate that the true support among all 10,000 parents is likely between, say, 64% and 76%. Inferential statistics is incredibly powerful for decision making, but it must be handled responsibly. The quality of your inference depends entirely on the quality of your sample and your methods. Always ask critical questions. First, how was the sample chosen? Was it truly random and representative, or did it overrepresent a certain group, introducing bias? Second, are we measuring the right thing? Does our survey question accurately capture a sentiment about the LMS, or is it worded in a confusing or leading way? And crucially, are we confusing correlation with causation? Just because two things happen at the same time doesn't mean one caused the other. Answering these questions ensures our statistical inferences are not just mathematically sound, but also meaningful and true. Now that we've covered the fundamentals, let's explore where statistics truly comes to life. It's not just a subject in a textbook. It's a powerful tool that shapes our world in countless ways, often behind the scenes. From the classroom to the doctor's office, from the ads you see online to the government policies that affect your community, statistics is the engine driving decisions and discoveries. Let's dive into the real-world uses of statistics and see where it shows up every day. First up, education. Educators are constantly tracking student growth over time. By analyzing test scores, assignment grades, and other performance metrics, they can see if a student is progressing as expected or falling behind. This isn't about labeling students. It's about providing timely support. For example, if a student's math scores show a downward trend, a teacher can intervene with extra help before the problem becomes a major roadblock. This data-driven approach ensures every student gets the personalized attention they need to succeed. Statistics is also crucial for analyzing test reliability and fairness. A reliable test gives consistent results. If you took it yesterday and again today, your score should be similar. Statistical methods like Cronbach's alpha measure this consistency. Fairness means the test doesn't disadvantage any group of students based on their background. By analyzing performance data across different demographics, administrators can identify and remove biased questions, ensuring that a test accurately measures knowledge and not cultural familiarity. It also helps in evaluating which teaching strategy improves outcomes. Imagine a school wants to know if a new project-based learning curriculum is more effective than traditional lectures. They can implement the new method in some classes and compare their students' final exam scores to those from traditional classes. Using a statistical test, they can determine if any difference in scores is significant or just due to random chance. This allows schools to adopt teaching methods that are proven to work. And finally, statistics is key for identifying learning gaps by grade level or topic. A school district can analyze standardized test data from all its schools. They might discover that fourth graders across the district are struggling with fractions. This insight allows them to allocate resources effectively, perhaps by providing specialized training for fourth grade math teachers or adopting a new curriculum supplement focused specifically on fractions. Next, let's look at business and marketing. Here, A/B testing is king. This involves testing two versions of something to see which one performs better. Companies use it for everything: ads, thumbnails, emails, and even pricing. For instance, Netflix famously tests different thumbnail images for the same show to see which one gets more clicks. By showing version A to one group of users and version B to another, they can statistically determine which image is more engaging and make it the default for everyone. Businesses also rely heavily on forecasting sales and demand. Using historical sales data, market trends, and seasonality, statistical models can predict how much product a company is likely to sell in the next quarter. This is vital for managing inventory. A clothing retailer, for example, uses forecasting to decide how many winter coats to stock. Ordering too few means missed sales, while ordering too many leads to costly overstock. Statistics are also essential for measuring customer satisfaction and retention. After you chat with customer support, you often get a survey asking you to rate your experience. Companies aggregate this data to calculate metrics like the Net Promoter Score. They analyze trends to see if satisfaction is improving or declining and identify common pain points. By fixing these issues, they not only make customers happier, but also increase the likelihood they'll stick around, which is crucial for long-term growth. And they're constantly optimizing operations using data trends. A shipping company might use statistical analysis to find the most efficient delivery routes, saving time and fuel. A factory can monitor its machinery for subtle changes in performance that predict a future breakdown, allowing for preventative maintenance. This field, known as statistical process control, helps businesses reduce waste, improve quality, and run more efficiently. Now for a field where statistics can be a matter of life and death: medicine and public health. Its most critical role is in testing whether treatments work. In a randomized controlled trial, one group of patients receives a new drug while a control group receives a placebo. Researchers then use statistics to compare the outcomes. Did the new drug significantly reduce symptoms compared to the placebo? Was the effect large enough to be clinically meaningful? This rigorous process is how we know which medicines are safe and effective. Researchers also use it for estimating disease risk factors. By studying large populations over many years, epidemiologists can identify correlations between certain behaviors or characteristics and the likelihood of developing a disease. This is how we discovered the links between smoking and lung cancer, or between high cholesterol and heart disease. This knowledge empowers both doctors and individuals to make informed decisions about preventative health. During a health crisis, statistics are vital for monitoring outbreaks. Public health agencies like the CDC track the number of new cases, hospitalization rates, and fatalities. They use this data to calculate the rate of transmission, identify hotspots, and predict the potential spread of the disease. This information is crucial for governments to issue timely public health warnings and allocate resources like vaccines and hospital beds where they're needed most. Finally, it's used for evaluating hospital outcomes and safety. Hospitals track a vast amount of data, from patient recovery times to rates of hospital-acquired infections. By analyzing this data, they can benchmark their performance against national averages and identify areas for improvement. For example, if a hospital notices its readmission rate for heart failure patients is high, it can implement a new follow-up care program and use statistics to measure if the program is successful in keeping patients healthy at home. A statistician's final word: data isn't truth. Its evidence data can be misunderstood, manipulated, or misread. Statistics teaches you to ask better questions like, is this result meaningful or just random? What's the margin of error? What's the sample size? Who was excluded from the data? Does this conclusion actually follow? That's how you go from numbers to knowledge.